So in this video we're going to look at some problems involving power for the differential equation topic. So this is the last type of question we need to look at before we go on to do exam questions, but before we look at some of those questions, it's important that I just recap power with you and work done, especially for those of you who haven't done physics. So in physics, work done is defined as force multiplied by distance. And the examples you see with work done involved in applied maths is usually where we have something like a car. And that car has an engine which applies a forward force which causes the car to move forward. Now, the amount of work that the engine does doesn't just depend on how much force, how much pushing force it is exerting on the car. It also depends on how far the car travels. So, for an example, if you had an engine which applies a force of 50 newtons and that engine pushes the car forward a distance of 5 meters, in physics the work done, I'll just put WD, is equal to the force multiplied by the distance travelled, which in this case is 50 times 5 or 250. And you can see from that equation that the further the distance, if S was increased to 10 meters, then more work has been done. 50 times 10, which is 500 joules of work has been done. So the unit of work done is joules, and you should recognize that because that's the same unit as energy. And that's because work done is actually the same as energy transferred. They're the same thing. It's just different ways of looking at it. So when the car has done 250 joules of work, it has also given the car 250 joules of energy. It has transferred 250 joules of energy to the car. And then energy might be kinetic energy, or it might be work against friction, where it has to overcome friction to make the car move. So there is different scenarios though. For example, we could have one car which applies a force of 50 newtons and pushes the car forward 5 meters. And then underneath that we could have another car which again pushes the car forward 5 meters and applies a force of 50 newtons. The first car A, might do this in a time of 5 seconds. The second car B, might do it in a time of 10 seconds. Now you might say, well, this is flawed because if it's the exact same force and the exact same distance, then how can the time be different? But just for the case of this example, let's assume this is true. There's obviously a difference in the way that they are working. And this car, the first car, is working a lot faster. So some of our equations or some of our calculations need to take this into account. And how we take this into account is something called power. And the definition for power is work done divided by time taken. And the unit for power is watts, which you've probably heard of before, a 100 watt bulb or 60 watt bulb. So for car A here, or the first car, its power is going to be 250 joules of work done. That's the 50 multiplied by 5, divided by 5 seconds. So its power was 50 watts. And for car B, the power is going to be 250 joules of work again, because it's the same force and the same distance, divided by 10, which is 25 watts. So what this unit tells us, or what power tells us, is that this first car is using up energy at a quicker rate, because another unit for power would actually be joules per second, because it's joules divided by seconds. So what this is saying is this car is using up 50 joules of energy, or it is doing 50 joules of work every second, whereas this car is only using or doing 25 joules of work every second. So there's two new equations for you if you don't do physics, or three new equations really. First of all, you have work done equals force times distance. So you want to remember that one. Secondly, you have the fact that work done is the same as energy transferred. And thirdly, you have this equation for power. So where does this come into differential equations? Now I'll do an example in a minute, but first of all you have to see how this applies to our differential equations. We know that power is work done over time. Now that's the same as the change in work over the change in time, or dw dt, or dwd if you want to say for work done. Now we have an equation for work done, and that equation for work done is force times distance. So this is the same as the change in force times distance all over the change in time. Now in all of the questions that you're going to be doing, force is constant. Not all of the questions that you're going to be doing, but all the questions which involve power. Or at least in the question they tell you that the force is constant. So if the force is constant, we can take the f out of our derivative, and this becomes f ds dt. And we know that ds dt is the same as velocity. So instead of power being written as work done over time taken, power can also be written as, not instead of, but also power can be written as force times velocity, assuming or given that the force is constant. So in the next number of questions you're going to be using these relationships that I've just gone through, so make sure you take a note of them, and then I'll do an example in the next video.